This is lecture number 15 of CS218 Data Structures and Algorithms. Assalamu alaikum. Today we are going to talk about stacks. We are going to use chapter 7 of book 1 for this topic. In the last lecture, we discussed the reasons behind preference of postfix expressions for computing machines. We traced through the algorithm for postfix evaluation. We traced through the algorithm for conversion from infix to postfix expression. And we investigated both time and space complexities of the algorithms that we discussed. In this lecture, we are going to talk about the application of stacks to the function of sorting. The algorithm that we will discuss is called Quicksort. So let us first talk about the structure of the algorithm. The Quicksort algorithm uses the divide and conquer strategy. In divide and conquer approach, the problem in hand is divided into smaller subproblems, and then each problem is solved independently. Since we keep on dividing the subproblems into even smaller subproblems, we eventually reach a stage where no more division is possible. These atomic smallest possible subproblems are then solved. The solution of all subproblems is finally merged to obtain the solution of the original problem. The quicksort partitions the sequence by dividing it into two segments based on a selected pivot key. Have a look at the algorithm for quicksort. Step 1. If the stack is empty, quit. Otherwise, pop a sequence from the stack. Step 2. Select the first element as the pivot, P. The location of P is called lock and is updated with P. Step 3. Begin from the right. Scan the sequence of keys from right to lock, looking for a smaller key than P. If you find it, swap it with P. Mark the new lock. Let this position be the new right. 4. Begin from the left. Scan the sequence of keys from left to lock, looking for a larger key than P. If you find it, swap it with P. Mark the new lock. Let this position be the new left. Step 5. Repeat steps 3 and 4 until left and right coincide. When they do, the pivot is at its correct position. On its left is a sequence L with all values less than P. On its right is a sequence G with all values greater than P. Step 6. Push L onto the stack, then push G onto the stack. Step 7. Go to step 1. The algorithm is in front of you on the left. There is a blue box at the bottom. This is my stack. It contains a sequence which starts from 0, ends at 11. So this means I have a sequence of 12 elements that I want to sort using the quicksort algorithm. The first thing I did was I popped the sequence from the stack, and this is the sequence unfolded in front of you. Why is there a red circle around 44? because I have selected 44 to be my pivot element. We can select any element to be the pivot, but to keep things simple, during this discussion of the algorithm, we will always select the first element to be the pivot. Lock marks the location of the pivot, so lock is at 0. Left is at 0, right is at 11. Start a scan from the right, looking for a smaller element than 44. 66 is not smaller, 88 is not smaller, but 22 is smaller than 44. So what do? We swap 44 and 22. This is what we get. You see that lock is now pointing to 9 because 9 contains the pivot. I had started the scan from the right and I scanned till index 9, so right is now at 9 and left is at its previous position. Now I will scan from the left, looking for a larger element than 44. 22 is not larger, 33 is not larger, 11 is not larger, but 55 is larger than 44. So this means that I am going to swap elements of indices 3 and 9. And I do that. 44 and 55 have been swapped. See that lock is now pointing to 3 because 3 contains 44. I was scanning from the left, so left has been updated and right is where it was. Now I will scan from the right, looking for a smaller element than the pivot element. So 55 is not smaller, 99 is not smaller, 60 is not smaller, but 40 is. So swap 44 and 40. This is what we get. Lock is now pointing to 6 because 6 contains 44. Right has been updated to the previous position of 40, which has now been swapped with 44. Now start scanning from the left, looking for a larger element than 44. 40 is not larger, but 77 is larger. So we are going to swap 77 and 44. This is what we get. Lock is now pointing to the new position of 44 and left has been updated. Start scanning from the right, looking for a smaller element than 44. 77 is not smaller, 90 is not smaller, and then what happens is left and right coincide. What does it mean? It means that 44 is now at its correct position, or 44 has been sorted. Now look at all the elements on the left side of 44. 22, 33, 11, 40. Are they sorted? No. What is common in these elements? All of these elements are less than 44. Look at elements on the right of 44. 90, 77, 60, 99, 55, 88, 66. Are they sorted? No. What is common in these elements? All of these elements are greater than 44. When the pivot comes to sit in its correct position, it breaks the given sequence into two sequences, one on the left, the other on the right. The one on the left is a sequence of values smaller than the pivot. The one on the right is a sequence of values greater than the pivot. What do we do with these sequences? We push them onto our stack. First we push the sequence of lesser elements. You see that the sequence of lesser elements, or L, extends from 0 to 3. So I push this sequence, or rather the upper and lower bounds of the sequence, onto the stack. The sequence of greater elements, G, extends from 5 to 11. And I push the upper and lower bounds of this sequence onto my stack as well. Why am I using the stack? I am using the stack to remember what sequences I still have to sort. So one element has been sorted. What do I do now? Look at my stack. Is the stack empty? No, the stack is not empty. Then pop a sequence from the stack. I pop a sequence and I get the sequence of greater elements from 5 to 11. I mark left at 5, right at 11. I take 90 to be the pivot element, so lock is at 5, the position of 90. Start scanning from the right, looking for a smaller element than 90. 66 is smaller. What do? Swap them. Now lock has been updated to 11. Start scanning from the left, looking for a larger element than the pivot, or 90. 66 is not larger. 77 is not larger. 60 is not larger. 99 is. So we are going to swap 99 and 90. This is what we get. You will see that lock has been updated to the new position of the pivot. Start scanning from the right, looking for a smaller element than 90. 99 is not smaller, but 88 is. So we will swap 90 and 88. This is what happens. Right and lock both are updated. Start scanning from the left, looking for a larger element than 90. 88 is not larger. 55 is not larger. And then what happens is that left and right coincide. Now when they coincide, this means that 90 is at its correct position. 90 has been placed in the position that it was supposed to be. 90 has been sorted. Again, two sequences break on both sides of 90. A sequence of lesser elements from 5 to 9 and a sequence of greater elements. But the sequence of greater element has only one element. When we were doing bubble sort, I told you that a single element is always pre-sorted. Look at the sequence of greater elements. It has only one element, 99. Do I need to sort this sequence? No, because this is just a single element and you never need to sort one element. So this means that 99 is also at its correct position. So this means that the only sequence that I have to sort is the sequence of lesser elements. This sequence extends from 5 to 9. So I push the sequence onto the stack. Now I look at the stack. Is the stack empty? No. I pop a sequence from the stack. This sequence is from 5 to 9. left is at 5, right is at 9, and the pivot is the first element, 66. So lock is at 5 too. Start scanning from the right, looking for a smaller element than 66. 55 is smaller, so I swap 55 and 66 and update lock. Start scanning from the left, looking for a larger element than 66. 55 is not larger, but 77 is. So swap 66 and 77. Left and lock have been updated. Start scanning from the right, looking for a smaller element than 66. 77 is not smaller, 88 is not smaller, but 60 is. So swap 60 and 66. Right and lock have been updated. Start scanning from the left, looking for a larger element than 66. 60 is not larger, and then this happens. Right and left coincide. This means that the pivot element 66 is at its correct position. This breaks our sequence into two subsequences, a sequence of lesser elements from 5 to 6 and a sequence of greater elements from 8 to 9. First we push the sequence of lesser elements onto the stack. And then we push the sequence of greater elements onto the stack. Now what to do? Is the stack empty? No. Pop a sequence from the stack. I get this. The sequence from 8 to 9. Left is at 8, right is at 9, lock is at 8, and 88 is the pivot. Start scanning from the right, looking for a smaller element than 88. 77 is smaller. Swap the elements. See that lock has been updated. Start scanning from the left, looking for a larger element than 88. 77 is not larger, and then right and left coincide. This means that 88 is now at its correct position. This breaks our subsequence into another subsequence on the left only, not on the right, because there are no elements to the right of 88. Now, the subsequence of lesser elements is also of only one element, and we have already discussed that a single element is pre-sorted. This means that 77 is at its correct position. So this means that no subsequence is going to break off. What do we do now? Look at the stack. Is the stack empty? No. Pop a sequence from the stack. I pop a sequence from 5 to 6. Left is set to 5. Right is set to 6. Lock is set to 5 because 55 is the pivot. Start scanning from the right, looking for a smaller element than 55. 60 is not smaller, and then this happens. Left and right coincide. This means that 55 is at its correct position. There are no elements to the left, but there is a sequence to the right. This sequence to the right has only one element, 60. This means that 60 is also in its correct position. So what does this mean? This means that I don't have to push any subsequences from this sequence onto the stack. Look at the stack. Is it empty? No. Pop a sequence from the stack. I get the sequence from 0 to 3. Left is 0, right is 3, log is 0 and pivot is 22. Start scanning from the right, looking for a smaller element than 22. 40 is not smaller, 11 is. Swap 11 and 22. You see that right and log have been updated. Start scanning from the left, looking for a larger element than 22. 11 is not larger, but 33 is. Swap 22 and 33. Left and log have been updated. Start scanning from the right, looking for a smaller element than 22. 33 is not smaller, and then left and right coincide. This means that 22 is at its correct position. This placement breaks two subsequences. The sequence of lesser elements has only one element 11, which means that 11 is also at its correct position. So I don't have to push this subsequence onto the stack. On the right of 22, I have a sequence extending from 2 to 3. So I will push this subsequence onto my stack. Look at the stack. Is it empty? No. Pop a sequence from the stack. I get the sequence from 2 to 3. Left is at 2, right is at 3, log is at 2 and 33 is the pivot. Start scanning from the right, looking for a smaller element than 33. 40 is not smaller, and then left and right coincide. This means that 33 is at its correct position. There are no elements on the left of 33. However, there is a sequence to the right. This sequence contains only one element. So this means that 40 is also at its correct position. So what do I do now? Is the stack empty? Yes. This means that I have sorted the whole sequence. Now if you look at the positions in which I left my different elements and bring those positions back, you will find this sequence: 11, 22, 33, 40, 44, 55, 60, 66, 77, 88, 90, 99, and the sequence has been sorted. This is Quicksort. Now that you have learned how to run Quicksort, run it for a sequence of 8 keys sorting in descending order. Then run the same algorithm for a sequence of 8 keys already sorted in ascending order. So the input that you are going to give to the algorithm, that input will be already sorted. I want you to see how the algorithm reacts to pre-sorted data. Having gone through quicksort, let us now look at the time complexity of the algorithm. Let us first focus on the best case running time. The best case of running time of quicksort happens when the correct position of the pivot is in the middle of the n element sequence in every pass. Two subsequences of roughly n by 2 length break off on both sides of the pivot in the first pass. Two subsequences of roughly n by 4 length break off on both sides of the pivot in the second pass. In the last pass, the two subsequences that break off on both sides have only one element. Let Tn be the time taken to sort n elements. Then the time taken to sort n by 2 elements must be Tn by 2. We compare the first pivot with n elements in the sequence to place it in its correct position, sometimes scanning from the right, at other times scanning from the left. And the correct position of this pivot is the middle of the sequence. So how many comparisons do we make to place the pivot in the correct position? N. Time to sort one element is constant. So we say T1 is 1. Time to sort n elements is number of comparisons to place the pivot in its correct position plus time to sort the subsequence of values lesser than the pivot plus time to sort the subsequence of values greater than the pivot. Mathematically, I can write it like this. Tn is n, which is the number of comparisons for the pivot, plus Tn by 2 plus Tn by 2. This is a recurrence relation. The base case is T1 equals 1. Rewriting it, Tn is 2 times Tn by 2 plus n. We will now solve this recurrence relation using backtracking. Tn is 2 times Tn by 2 plus n. Focus on Tn by 2. I am substituting the value of Tn by 2. Tn by 2 can be written as 2 times Tn by 4 plus n upon 2. I substitute this value in the first equation that you see here. And the final equation is 2 raised to the power 2 Tn by 4 plus 2n. Now, in the second equation, focus on Tn by 4. This can be written as 2 Tn by 8 plus n by 4. I substitute this in the second equation. And the third equation says Tn is 2 raised to the power 3 Tn by 8 plus 3n. Now look at the three equations again. There is a pattern. In the first equation, I have 2 raised to the power 1 Tn by 2 plus n. In the second equation, I have 2 raised to the power 2 Tn by 4 plus 2n. In the third equation, I have 2 raised to the power 3 Tn by 8 plus 3n. Generalizing for k, we can say that Tn is 2 raised to the power k, Tn by 2 raised to the power k plus kn. The base case is T1. We want n upon 2 to the power k to be equal to 1 so that we can substitute the value of the base case here. So if n upon 2 raised to the power k is 1, then n is 2 raised to the power k, or k is log n. So this is our equation, and we substitute k equals to log n in it, and we get this equation. Now, the value inside the bracket with t will become 1, which is our base case. And t1 is 1, so we substitute the value of the base case. And Tn is n plus n log n. The best case of quicksort has a time complexity of O n log n. Now we will talk about the worst case running time of quicksort. The worst case of running time of quicksort happens when the sequence is already sorted in ascending or descending order. The correct position of the pivot is at the first or the last index of the sequence in every pass. The longest possible subsequence breaks off every time. Let the sequence be sorted in ascending order. A subsequence of n minus 1 length breaks off on the right of the pivot in the first pass. A subsequence of n minus 2 length breaks off on the right of the pivot in the second pass. And this continues until we have just one element breaking off, and obviously that is sorted. Let Tn be the time taken to sort n elements. Then the time taken to sort n minus 1 elements must be Tn minus 1. We compare the first pivot with n elements in the sequence to place it in its correct position, which is the 0th index of the sequence. Time to sort one element is constant, so we say T1 is 1. Now, time to sort n elements is number of comparisons to place the pivot in its correct position plus time to sort the subsequence of values greater than the pivot, because no subsequence of values lesser than the pivot is breaking. This can be mathematically written like this. Tn is n plus Tn minus 1. T1 is 1. Rearrange it and write it this way. Tn is Tn minus 1 plus n. Again, this is a recurrence relation with base case T1 equals 1, and we solve it using backtracking. So Tn is Tn minus 1 plus n. Focus on Tn minus 1. By recursive definition, I can write it like this. Tn minus 1 is Tn minus 2 plus n minus 1. And the equation that I get is Tn minus 2 plus n minus 1 plus n. Let us continue the trend. Tn minus 2 can be written as Tn minus 3 plus n minus 2. I substitute this in the equation. Again, we see a pattern. First, I have Tn equals Tn minus 1 plus n. Then I have Tn equals Tn minus 2 plus n minus 1 plus n. Then I have Tn equals Tn minus 3 plus n minus 2 plus n minus 1 plus n. Generalizing for k, we can say that Tn is Tn minus k plus n minus k minus 1 all the way to n minus 1 plus n. This is an arithmetic series. There are k terms in this series from n minus k minus 1 to n minus 0. The sum of this series is given by the formula of summation of an arithmetic series. Number of terms divided by 2, the first term added to the last term. I have used this formula to get the summation equal to k by 2 to n minus k plus 1. I can replace the whole series in the orange box with this summation. And I do this replacement. Look at what we have with t. We have t n minus k. I want to place 1 here so that I can apply the value of the base case. We want n minus k to be equal to 1, which means k is n minus 1. Putting k equals n minus 1, this is what we get. Substitution of the value of k. Simplify it. Tn is t1 plus n minus 1 whole divided by 2 times n plus 2. I have substituted the value of t1. Now I can say that the worst case of quicksort has a time complexity of O(n) squared. So what did we learn today? We were introduced to the quicksort algorithm. We traced through the quicksort algorithm and we investigated the time complexity of the algorithm in best and worst cases. At the end of this lecture, I ask you to read the book, do the homework. I will be giving you an implementation of the quicksort algorithm in Python. Run that implementation and see if you understand it. Note your questions, and if you have any suggestions, email them to me. Do show me your homeworks. Take care. Allah Hafiz.